section 12.5, which is on normal distributions. So normal distributions are also called the bell curve. So you might have seen these before. So what group is studying the bell curve right now? You're in that group. Have you guys found things that are normally distributed?
Yes.
Lots of things, right? So you could talk about the height of all the people in this class is normally distributed. The height of all men in the United States, the shoe sizes of all women in the United States. Like everything is normally distributed. So basically if you have an average, and then there are outliers. So there's some people that, maybe if I'm talking about the heights of all women, there are women that are like 6'5", right? But they're outliers. They're probably not very close to the average height. Does this make sense? Okay, so in order to compute these normal distributions, we need what's called the standard normal table. So this is the standard normal table. You will have this for your test. I'll print it for you. You don't have to memorize every number on that page. Isn't that nice? Yeah, that's really nice of me. All right, so let's do some examples. So it says, suppose the mean of data is 0 and the standard deviation is 1. So if you remember from last time, we write mean with a mu. So mu is 0, and standard deviation is sigma. So sigma is 1. And if you notice, that's what this standard normal table says. It says the mean is 0 and the standard deviation is 1. So for each of these problems, we're going to draw our beautiful bell curves. So we're going to draw a bell curve. And in the middle, we have our mean is equal to 0. So what this says is the probability that x is greater than or equal to 0. Well, 0 is where our middle is. Our mean is equal to 0. So if I'm greater than or equal to 0, I'm shading this portion. And in many ways, it's very similar to our geometric probability problems. Like when we said, we have a square, and inside we have a circle. What's the probability of landing in this shaded region? And it was like here. So we found the area of the shaded region, and we divided by the total area of that square. Do you guys remember those? Same idea here. So what do you think the probability of landing under that bell curve, but on the shaded side would be? 50%, exactly. So if you look at this bell curve, the standard normal table, we have these values here. We're going to go down to 0.5, or not 0.5, or down to 0, 0.0, and it says 0.5. Okay, so that's saying on this bell curve, if I shade up to the 0, 0, we get 0.5. But notice our other side was on the right side. Is that okay? Yeah, it's still 50% as well. Okay. So this one says the probability that x is greater than or equal to 1. So we draw our bell curve, and we have x is equal to 1 is on this side of our mu, which is 0. And we have everything greater than or equal to that.
How exactly do we know where x equals 1 is?
You don't have to be like super precise with that. Just draw it on the right side. Because we know 0, if this was x equals 0, it's in the middle. So we're on the right side of that. Kind of like a number line. So if I have x equals 1, we look in our chart. We look for 1.00. Do you guys see where 1.00 is? We go over to 0, 0, because it's 1.00. And we get the area of 0.8413. So kind of like 84%, 0.8413. Which side do you think is 84%? Do you think it's on the left side of the line, this side, or do you think it's on the right side of the line?
The left side.
The left side. Why do you think it's the left
That's
side?
the bigger one.
Yeah, because it's more than half, right? So 0.8413, is that what it was? Is on the left side of the line. So we need this other side. So think about how we would find that. Yeah, subtract it from 1. Now, some of you guys might have trouble doing that without a calculator, but I know right away that it's 0.1587. Do you guys know the trick for doing that? Think about it.
How are you getting these numbers?
I'm doing 1 minus the 0.8413, and I'm telling you it's 0.1587.
But I mean, how are you finding the point?
I found the 0.8413 in this table. I went down to 1.0, and it was right here. So these are the probabilities in here. These are the x values. We'll do a lot of them.
But then shouldn't all the zeros be 0 if there's a 0 probability that something will happen?
I don't know what you're saying, but we'll do lots of examples. I'm sure it will click. All right, so we have 0.1587. So the easiest way of doing this is to do this in your head is to find every number that's going to add to be 9. So 8 plus what gives you 9? 1. 4 plus what gives you 9? 5. 1 plus what gives you 9? 8. And then the last number you want to make 10, so then all those are rounded up. Does that make sense? So you're adding them up to be 9, 9, 9, 10. All right, so this next one, a little bit harder. Okay, so now we have two numbers, and we're saying what's the probability that we're between negative 1.2 and 1.5. So now we have this shaded region. Okay, this is the hardest that they are. So the whole section, this is about as hard as it gets. Okay, so let's see if we can get it. So notice on our chart, we don't have any negative numbers. We only have positive numbers. So let's do the 1.5 first. So we're going to go down to an x value of 1.5, all the way down. You guys see 1.5? And the second decimal, 1.50, right? So we're going to use 1.50. So I get point, what is that, 9332? Okay, whoops. So that means that the area under this curve, all the way this way, so sometimes I draw like a little arrow above it, is 0.9332. Okay, but we want to take something out. We want to get rid of this extra little piece on the left-hand side. So in these types of problems, what I do a lot of times is I find the tails. So this tail is going to be 0.9332 subtracted from 1, right? 1 minus 0.9332. Can you do the trick in your head? It's going to be point what? 0.0668. Yes. Do you guys see it? You can also do 1 minus on your calculator, 1 minus 0.9332. So we have that. Okay, now we need that negative 1.2. So there are negatives on the chart, right? So let's look. So if I look up positive 1.2, I get 0.8849. So here's our dividing line, the 1.2. We have this dividing line here. Do you think the left side of that is the 0.8 number or the right side of that is the 0.8 number? The right side. Do you guys see how that's more than 50%? So what was it, 0.882? What was it, 0.8 what? 8849. I don't even know what number it was. 0.8849. Do we have that number? Okay, how do we get its tail? 1 minus that. So when we do 1 minus that, we get 0.1151. Exactly. So how do we get the shaded region then? Exactly. Perfect. You guys see it? We do 1 minus 0.1151 and also minus 0.0668. Okay, that's the only one that I think you'll need your calculator on. But you could probably do it off to the side too. Oops. Ah, jeez. I'm just clicking the wrong buttons here. 0.8181 is the answer. Okay, does that make sense? Now there are lots of ways that you can do that problem. So some people don't find both tails, they just find one of the tails. Because then they say, oh, if I take this number and I subtract out this tail, right, you get the same thing. Does that make sense? You can do it that way as well. Does that make sense? All right, so let's try another one. So the probability that x is greater than 2.4. So we're going to be on this side. And if you look at your standard normal table, 2.4 is way, way down there. 2.4, 0.9918. So that 0.9918 is this side of it, 0.9918. So we want the other side. So we do 1 minus 0.9918, and we get 0.0082 is our answer. Okay, do you guys understand this process? Yeah. Okay, yeah?
How exactly are you using the numbers from the table to put in and figure out these? I mean, for the second one on 3, where you found the 0.1151, how did you associate it with the other tail?
So basically these are like areas under the curve where the most area is 100%. So we're thinking of like percentages, kind of like probability. So if the whole thing's shaded, it's all 1. If half of it's shaded, it's 0.5. So I could have that side, or I could have this side. This would be 0.5. So what we found on number 3 is we found the area all the way up to here. So from here over was this number 0.9332. So if it adds up to be 1, this has to be the rest of it. It has to be 1 minus 0.9332. And that's how we got that 0.0668. So you can subtract it out and get that.
Okay.
So we're thinking about them as percentages. What percent is filled in? Yeah.
Does it matter if it's greater than or equal to, or just greater than?
It doesn't. So he's noticing that this says probability that x is greater than or equal to 2.4. It could be greater than or equal to or greater than. It doesn't matter because the probability of landing exactly on 2.4 is 0. I know, that's weird, isn't it? So, all right, so the probability of x being less than negative 1.18. So try it along with me. Be active note takers, right? We've talked about this. So we have our 0 in the middle. 1.18 is negative, so it's on the left-hand side. And we want x is less than that. So we want to shade on this left-hand side of it. So we don't have negatives on our chart, but we do have positives. So we're going to look up 1.18. Now this is the first one I've given you where there's a second decimal. So we're going to go down to 1.1, which is right here. And we're going to go over to 1.18. That's right there. So you should get 0.8804. Does everybody see that in their chart? So follow it along with your finger. Make sure you see it.
So then is the top chart for the last decimal point?
Yes.
So that is all that that's for?
Yes.
Oh. Okay.
So we had 0.8804, and that's going to be which side? The left side or the right side? Is it a big area or small? It's a big area, right? So we're going to do 0.8804, and what we want is the smaller area. So we end up doing 1 minus 0.8804, so we get 0.1196. You guys all see that? Make sense? All right, so this is another one where there's tails. Do you guys want to try it first? All right, so try it. So this first one, so we're going to look up some different numbers on the chart. So these ones are actually both on the right-hand side, right? Did you guys have that sketch correct? So here's the part we're trying to find. And when we look up 1.54, we get a certain probability. What do we get? 9382. Okay, and then we could find that tail. So if you found the tail, you would get 0.0618. Did you guys have that? 0.0618. Okay, and then if I want the other side, well, I can look up 1.23. And what do I get when I look up 1.23? 0.8907. And I could find the tail for that one as well. Well, that is the tail, right? I guess we're good. So how do I get my final answer? Well, I could use that. I could do 1 minus 0.8907, the first tail, minus 0.0618, or I could do it another way in this case. So Nat, what did you do?
Can you subtract 0.8907
Yeah, do 0.9382 minus that 0.8907. It gives you the same answer, which is what?
well, I did it wrong the first time.
So what do you guys get for your answer? What is it? 0.0475. Did we all get that? Is that right? I don't know. I didn't do it. So tell me if it is or not. Yeah, so good. All right, so you can do the method where we subtract out both tails, or you can just say, well, this part was the big part. I'm subtracting out the smaller part to leave that shaded region, right? That works as well. All right, so unfortunately, all data does not have a standard deviation of 1 and a mean of 0. So if I talk about the average heights of all women in the United States, the average height is not 0, right? So we have to change it so that we can use this table because we don't have an infinite number of tables we use. There actually are a lot of tables that we use. So some of the tables in the AP Stats book don't have this portion shaded, the left side shaded. Instead, they have the right side shaded, and then it's all these 1 minus numbers, right? So you can have different charts, so make sure you know what you're using, which chart you're using. But in this case, we're going to have something that we're calling z-scores. So we have x values that we need to change to z values. And if you notice on your chart, you guys see how it says z. We want things to be z-scores. And so what I'll give to you guys is I'll give you the chart, but I'll also give you this equation. And it's going to say, z is equal to x minus mu over the standard deviation. So this is what we're going to use to convert any problem into a standard normal problem. So something we can use the chart on. Okay, so let's look at these. So it says the x or z value of the data set with mean m and standard deviation sigma is z equals x minus mu over the standard deviation. So basically when we have the original curve, we use x's, but if we change it so we can use our chart, we change them to z-scores. So this problem says, as the SAT is used for college admissions, if you want to go to grad school, you have to take a test called the GRE. And the GRE has a verbal section, an English section, and a math section, a quantitative section as well. All right, and it says a sample of the quantitative scores and verbal scores are both normally distributed, so there's kind of an average score for all the students. And then there's a standard deviation. So it says Natalie scored a 610 on the verbal section and a 700 on the quantitative section. So which test did she do better on, the English or the math? The math. It looks like she got a 700 on it, right? So let's see if this is true, if she really did do better on the math. Because maybe her percentile score, the number of people she's scoring better than, is higher. So we want to know what her percentile is. We want to know if she got in, you know how you take like the ice step when you're a kid and it's like, you scored in the 92nd percentile, and you're like, woo! That means you scored better than 92% of the people that took the test, okay? So let's figure this out. So let's talk about the verbal and the quantitative. So our verbal section had a mean of 470 and a standard deviation of 121. And it says that Natalie scored higher than the mean, because the mean was 470. She scored a 610. So we want to find the percent of people that scored lower than she did. That's her percentile scored. So we want to shade on the left side. Okay, so in order to do this, we can't use 610 for our number, because if you go back to our standard normal table, look at 610, where that would be. The chart only goes up to 2.9. So going up to 610, ugh, something's wrong, right? So we need to change this into what we call z-scores. So what was the mean of our standard normal table? The mean should go to 0. So if I plug this mean, this 470, into my equation, this z is equal to x minus the mu over the standard deviation. If I plug in 470 for x, 470 minus the mean is 470 over standard deviation, it changes it to 0. Okay, so our mean is going to now be 0.
Is the mean always 0?
Yeah, if you change it to your standard normal table. And if we're changing our z, or our x value of 610 into a z-score, we subtract 470 from it and divide by the standard deviation of 171, or not 171, 121. So 610 minus 470 divided by 121. And I get 1.57024793. What do you think I want to round to for this chart? 1.16. Exactly. I want 2 decimals because the chart only has 2 decimals in it, right? Normally I'm a stickler for 3 decimals. You know that. All right, so that's what we're going to use. We're going to use 1.16. So now we've changed all of our numbers, so now we can do exactly what we did before. That's all we're doing. We're just changing our numbers so we can use this chart. So we go to 1.16 on our chart. So go down to 1.1 and then go over to 1.16. So it says 0.8770. So that's what the area under this curve is, 0.8770. So that's our probability. So what does that mean for her percentile?
She's in the 88th percentile.
Yeah, we actually say the 87th because she's still within the 87th percentile. She's between 87.0 to 87.9. So we're going to say the 87th percentile. She's in the 87th percent. But I would be fine if you guys rounded up to 88. Okay, does that make sense? Do you guys understand that process? Okay, so let's do it for the quantitative one. So we still have our mean is 550. Our standard deviation is 148. So for this bell curve, we have 550 in the middle, which we're going to change to 0. And she scored, what'd she score on this one? 700? So we want to find the percent of people that were scored below her. So we change these into x values. So this mean changes into 0, and this, sorry, not x values, we change them to z-scores. This x is changed into, so we have 700 minus our mean was 550 this time, divided by our standard deviation was 148. So 700 minus 550 divided by 148, so I get a z-score of 1.01. Make sense? Now we look that up. So we go back to our chart, and we look up 1.01, and it looks like 0.8438. Do we all see that number in the chart? So the probability is, what did I say, 0.8438. So what percentile? 84th percentile. So which one did she really do better on? Yeah, kind of like the math one, right? She scored higher on the math because she scored better than all those people that took it. Okay? Does it make sense? I think it's kind of weird when you first see it. All right, so let's try some random questions here. So it says, a normally distributed data set has a mean of 74 and a standard deviation of 8. Find the probability that a data value chosen at random is between 66 and 78. So we sketch it out. So we're like, okay, our mean is 74. Our standard deviation is 8. And we're finding our probability that we're between 66, which is going to be on the left-hand side, and 78, which is on the right-hand side. And then we're shading in between. So we want to change both of these into z-scores. So we're going to have our x value, 66, minus our standard our mean, which was 74. So 66 minus 74 divided by 8. So I think I get -1, right? -8 over 8, so -1. And then same thing here. Our z-score is 78 minus 74 divided by 8. So I get 0.5. So it's really the same as when we first started class, and we were just taking our mean was 0, and we had 0.5 and -1. We're doing exactly the same thing. These are now z-scores, so we can use our chart. So let's look up 0.5. So when you guys look up 0.5, what did you guys get?
0.6915.
Yes, we got 0.6915. So can we find that little tail then? The rest of it? Yeah, that's going to be the number 0.3085. Yeah. Do we see that? Okay. Now let's say we look up 1 in the chart. Well, when we look up 1 in the chart, what do we get? 0.8413. So can we find this tail then? What's the rest of it? 0.1587. So how do we get our final probability?
How did you get the middle if you couldn't figure out what the first one was in the first place to get the first one?
I don't have the middle. I have from here over all the way this way.
How did you find that out?
I looked it up in the chart using -1. So I used 1 on the chart.
Oh, so you can just use 1, and if it's,
Mhm.
if it's negative,
And think about which side it's on then. Yeah, if it's negative, so you want to big side, little side, right?
Just flip it.
So our final answer is 1 minus the 0.1587 minus the 0.3085, those two tails. So what do we get? Jacob, help me out. Do 1 minus 0.1587 minus 0.3085. Did you get it?
What?
Do this for me.
1 minus
Did you guys all get that? 0.5328? Okay, perfect. Do you guys see it? So we're just doing one step at a time. You're changing your x values to z's, and then we're doing what we did at the beginning of class. Okay? So let's try a couple more. So I'm going to skip around here. So let's try like number 5. So it says a radar unit is used to measure speeds of cars on a highway. The speeds are normally distributed, that means bell curve, with a mean of 70 miles per hour and a standard deviation of 10. What is the probability that a car picked at random is traveling more than 75 miles per hour? Probably pretty good if you're on 465. All right, so our mean is 70. And we want to find the probability that we're greater than 75 miles per hour. So we're finding the right side of this bell curve. So we can't look up 75 in our chart. That's an x value. We want to change it to a z-score. So we take that and we change it. We do 75 minus our mean was 70 divided by our standard deviation, which is 10. So we get 0.5. So that's our z-score. So we look up z equals 0.5 on the left side of our chart. And then we find the value that goes with it. I think it's like, is that the, it's a point something, 0.69. 0.6915. Did you guys have that? Okay. So that's more than 60%, right? It's more than 50%. It's that whole left side. The rest of it is the part that's in blue. So that's when we do our 1 minus. So we're going to do 1 minus 0.6915. So I get 0.3085 is our answer. Now, if I wanted to write this very math-wise, like this is probably a good thing for like AP stats if you're going into that, here's how I would write it. So I'd say the probability that our x value is greater than 75 is the same as the probability that a z-score is greater than 0.5, which equals 0.3085. That would be the correct way of writing that. Does that make sense? All right, and then the last type we have is when we go from our probability and we go back to a z-score, which then goes back to an x-score. So let's try one like that. So number 6 says, entry to a certain university is determined by a national test. The scores on this test are normally distributed with a mean of 500 and a standard deviation of 100. So we have our mean is 500, our standard deviation is 100. Tyler wants to be admitted to this university, and he knows that he must score better than at least 70% of the students who took the test. So part A is just like what we've done. It says he takes the test and he scores a 595. So if the mean was 500 and Tyler got a 595, we're going to figure out what his percentile score was. So we take this number and we change it to a z-score. So we do 595 minus the mean is 500 over the standard deviation of 100. So I get 95 divided by 100, which is 0.95. And we look that up in the chart. Can somebody look that up for me in the chart so I don't have to click back to it? 0.8289. We're trying to find this area here, and that's what it is. It's 0.8289. So he scored in the 82nd percentile. Did he score better than 70% of people that took the test? Yeah. So will he be admitted? Yeah, he got an 82.89%. I would hope that he is admitted. You never know. All right, so let's say you want to do the bare minimum, and he's like, I only want to go to this school. I only want to score in the 70th percentile. I'm only going to try to get the 70th percentile. I'm not going to study. Probably not the best way to approach things like that with college admissions. But we're saying, well, what if the mean's 500, and he wants to get in the 70th percentile? That means that we want this area in here to be 0.7000. Do you guys understand what I'm saying? We're going backwards. What z-score would he need to get that? Well, we go back to the chart, and now we're looking in the probability area. We're looking in the percentages, which is this area here. And we're trying to find 0.700. Now, I don't have an exact 0.700, but I have 0.6985, and I have 0.7019. Which one do you think we should choose? I mean, one is closer. The 0.6985 is closer, but is he going to get admitted if he gets the 69.8%? Probably not 69.85. So let's pick the 0.70 and 19 just to be safe. Now you could be fancy. What else could you do, Jacob? I bet this is what you would do. You could pick a number that's between, and you could do 0.5 to 5. You could do that even. I would accept that. But let's say we go with this 0.7019, which is a z-score of 0.53. Do we see that? So we go back here and we're like, oh, the z-score is 0.53. So is that the score he needs on his test?
Nope.
0.53? No, that's the z. So now we need to find our x value. So we use that equation. So we say our z-score is equal to x minus mu divided by the standard deviation. And we say, oh, his z-score was 0.53. The mean was 500, and the standard deviation was 100. We solve it. We multiply the 100 over. We get 53 equals x minus 500. What score does he need?
553.
Yeah, he needs a 553. That's it. So sometimes you might have to go backwards. So I don't have a ton of those, but I think I do have one or two on the test or on the homework like that. All right, so let me stop there. I'll pass it out.